Hello everyone and welcome to this lecture in which we will see how with the aid of a computer we can make calculations of thermodynamics. So, for this purpose we will make use of a software called as EES, which is the abbreviation of Engineering Equation Solver. So, you go to www.fchat.com/EES and then you have a page where you can download a demo version of it. A demo version of it has various limitations, but for our purpose, for what we intend to do, we intend to make use of various properties and do some calculations. The idea behind EES is to not have a black box. It doesn't solve everything for you. The thing is, you have to tell what it needs to do, you have to tell what properties it needs to fetch, and then it will look up the database. The database typically one would read from a book. There are tables of data corresponding to this temperature, this pressure, this energy and all these things. So, instead of doing that manually, the computer does the lookup for you, and then what you do on a calculator can be done on this software. This software has various other abilities. It can do single variable optimization, it can solve ODEs, it can do nonlinear equations and so on. It is a very robust and flexible software, but the demo version we will use primarily for this academic purpose for learning various concepts of thermodynamics. So, when we go to the demo, when we click on the demo, it is inside downloads. It opens this page where you have to do a quick registration for EES on Windows. So, you put in the details, okay. And you use it for educational purpose, because if you want to use it for professional purposes, you need to buy the software. Then you click on I am not a robot, and then the whole AI business starts. Nowadays that is a big thing. So, with fire hydrants, okay, good, I am not a robot, and then you submit. So, download a working demo. So, click here to download. So, let us click over there. So, then we save it on our desktop. You can save it wherever. Then we go to the folder and then we install the software. That is as easy as this. You can change the path of installation as you like. It is a very flexible software. And then it opens up this screen. So, demonstration version for evaluation purposes. This demonstration version is limited to only 50 equations, but 50 equations, as you will see, is a lot of equations. Okay. So, first things first, let us create a new file. So, this is how the intro screen looks like. So they have also given us a small example of x square plus y cube equal to 77. So, let me try to first increase the font. We go to options, preferences, font size, let us make it 18, yeah, that is more like it. So, let us create file, new, and let us paste this. Okay. So, the thing is, the copy, paste, cut, print, these options have been disabled in the demo version of this EES. Of course, the complete version of EES does support all these operations, but as a penalty for the user to use a free software, the free version of the software, they have disallowed us to do all these things. But anyway, let us see how an equation, a nonlinear equation can be solved. So, let us say we have these equations x square plus y cube equal to 5 and x minus y equal to 2. We have written down the equations in the equation window, and then we have to go to this icon, which is solve. Calculations completed, 2 equations in one block, and it shows you that the residual is this. The fact that it is showing a residual implies it is using some kind of a nonlinear solver, and thus the solution obtained is x equal to 2.233 and y equal to 0.2332. Okay. These two are the solutions for this nonlinear coupled equations. So, it does not matter what order you input your variables as, but as long as it has the variable, as long as it has the equations, it will solve it. So, in the case of thermodynamics, it has various inbuilt functions. Okay. Let us try to do a very simple example. Let us try to determine the pressure. So, the comments so because it is a demo version, it will not let me save as well. The comments can be written in curly braces. So, if you run this thing becomes blue. If you buy the full version, of course, you can save the file. Okay. So, we open a comment and then we write the nature of the problem. It is for us to understand. The more comments you write, the better it is for others to understand what you are trying to actually do. So, the question is, determine the pressure for water at 200 degrees Celsius with V equal to 0.4 meter cube per kg. So, in this particular problem, we have to find the pressure of water for which the temperature is given and the volume is given. So, if you have to do this by means of the manual tables, you would go to the table and then first you would have a look at what the properties are at 200 degrees Celsius. So, one would check if V equal to 0.4 meter cube per kg lies between the specific volume of vapor and liquid. Essentially, you would check if 0.4 lies between this particular point and this particular point. Is 0.4 over here, or does it lie somewhere between the vapor and the liquid? If yes, then the fluid is in a two phase region. Okay. If no, then we have to check if the volume is larger than this or smaller than this. If it is larger than the saturated vapor volume, then we know that the final solution corresponds to superheated zone. If it is less than that, it corresponds to a subcooled region. So, in order to do that, you have to first look up the saturated tables, determine if V equal to 0.4 is actually a saturated property or not. If it is in the superheated zone, you would then make use of the superheated tables and determine then the temperature, the pressure. But here in ES, we would simply write P is equal to pressure, vapor, T equal to 200 and V equal to 0.4. Steam is not vapor, it is steam. So, it gives an answer of 530.4. But what are, I mean, how do you make sense of anything? What is 530? Okay. So, in order to do that, one has to see what the units are. So, you click over here, it gives you a window which shows the preferences. So, the unit system is SI units. See, the older books and older systems of engineering, sometimes they follow English systems, pounds, foot and all these things, but we do this. Specific properties is on a mass basis. See, specific volume is the total volume divided by the total mass. So, you can also have specific molar volume, which is the total volume divided by total number of moles. However, if you select that, then only it becomes on a molar basis, but now we are working in a mass basis, because that is what we have followed in the theory class. The temperature units, it is in Celsius. This is the very important step. Okay. Ideal gas equations and all this work in Kelvin, but typically for engineering one works with Celsius. The pressure units are kept as kilopascal, very important, because typically what the pressures are used, you will report them as either kilopascal or megapascal. Rarely will you use pascal or bar as the unit. Sometimes you can use bar also, but usually it is kilopascal or megapascal. For example, the atmospheric pressure is 0.1 megapascal or 100 kilopascal approximately. So, the energies are also reported in kilojoules and the trigonometric functions are used in degrees. See, these are what naturally we write, 60 degrees and all this. Okay. So, Celsius and kilopascal are the more important things to be noted right as of this moment. So, thus the output pressure that we obtain over here is in kilopascal. So, the answer is 530 kilopascal, 530.4 kilopascal. But wait, so we want to actually observe where this point lies in the PV diagram or the TV diagram. So, instead of writing T as 200, so 200 was a degree Celsius, that is why we wrote 200 and not, we did not convert the temperature into Kelvin, because we are naturally using the units as degree Celsius. Even in the tables of the book, you will use degree Celsius as the unit. So, let us write this as T1 and let us write this as V1, where we have declared everything as an array now. Okay. P1 is the first element of the P array, T1 is the first element of the T array, V1 is the first element of the V array. Actually, to avoid any confusion, let us write this as temp, let us write this as vol and let us write this as press. See, because inside this function, so pressure is the name of the function, this is the name of the keyword. This keyword is what tells that look up the tables of steam. This is the keyword which tells the function pressure that look up the steam table whose temperature I am giving you. That is why T equal to. See, later on we will see that we can use enthalpy, entropy, internal energy and all these things. So, that is why you need to tell the computer that which property do you want to use to calculate the pressure. In this case, you will use temperature and volume, hence V equal to vol 1. So, let us define temp 1 as 200 and vol 1 as 0.4. After running this, we obtain an arrays table where we have the first entry of pressure as 530.4, the first entry of temperature as 200 and the first entry of volume as 0.4. We can now plot this. We go to plot, we go to new plot window, we go to XY plot. In XY plot, suppose we want to plot Okay. So, before this we actually need to draw a property plot, because we want to superimpose this particular point on a property plot. So, we go to plots, we go to property plots, then we have to select what kind of fluid we want. So, we will go to water or steam. Okay. We are working with steam. So, then we want to select the type of property plot that we want. So, let us do it in a TV plot. Then additional things that you have include lines of. Okay. So, let us deselect these for now. So, these are isoentropic points, isoentropic lines, these are isobars. In our particular case, let us draw one particular isobar, or let us draw two particular isobars, one at 500 kilopascal and one at 400 kilopascal, because we already know that the solution is 540 point something. So, let us draw the two isobars, it will help us to understand where the point lies in a better manner. Okay. We deselect show lines of constant quality as well. So, once we press on OK, it will create this particular figure. Okay. So, on a TV plot, this is the isobar corresponding to 400 kilopascal, and on top of that is the isobar corresponding to 500 kilopascal. Okay. The volume is in a log scale. If you do not do this, the plot will look very odd. We can change the x axis limits from 10 raised to minus 3 to 1, because we do not really bother about this region. So, let us double click on this, we go to y axis, the x axis, and the maximum we call it as 1. So, now it has rescaled the plot for us. Similarly, on the y axis, let us draw it till 400. So, the minimum is 0 and the maximum is 400. Let us say that the minimum is also 100. So, this is how the plot looks like, very neat, very good. So, this point is 500 kilopascal, this is 400 kilopascal. Now, let us overlay the array points that we had just obtained. See, we have declared everything inside the array. So, now we can choose these points and plot it on top of this property plot. So that we can know exactly where that point lies. So, we go to plots, overlay plot, and on the x axis we need the volume. So, we select vol I, on the y axis we have temperature, temp I, and we denote the point as a symbol, as a filled square of color blue. There you go. So, this corresponds to 540 kilopascal. It is above the 500 line. So, ideally we should have plotted another line. So, anyway we can do that. We can do another plot in which we add, let us add the 540 kilopascal line as well. Let us add 600. Okay. TV, this is the new plot, that old plot window is still over here, we can get rid of it. On this new plot, we quickly readjust the axis. So, the middle line is 540, and then on this plot we can do a plot, overlay plot. On the x axis we have the volume, on the y axis we have the temperature. We plot it as a blue square and it lies on the isobar. So, clearly this point that we sought is corresponding to 200 degrees Celsius and corresponding to a specific volume of 0.4. So, look, this temperature, this particular temperature is 200. Okay. So, it does lie on the 200 degree Celsius line and it corresponds to a volume of 0.4. This is 0.1, 0.2, 0.3, 0.4. It is a log scale. This is 0.4. So, this is how we have obtained the coordinate where that point actually lies, and this black solid line is the two phase region. Anything inside that, anything inside this is the two phase zone, and clearly our point lies in the superheated region. So, the corresponding point is in the superheated region. Now, suppose someone asks me, that is all well and good, I want to know what is the specific volume of vapor corresponding to this particular temperature. Okay. So, I write down temp 2 is equal to, so I want to know what is the specific volume. We have already discussed that if the pressure is known, then if I want to know this, I cannot use temperature as the other property, because temperature and pressure inside this region are not independent. I can only use the volume, and I need to know exactly what the volume is. That is what I am seeking. At the just obtained pressure. Let us comment this first, because I want to pull up the plot. This was the plot which we had obtained. Okay. So, now I want to know that now that I have found the isobar corresponding to this 200 degree Celsius and 0.4 state, I want to know what this particular state is. This particular state corresponds to whatever pressure we have just found, because this line is an isopressure line. Okay. And I want to know what is this particular volume, and thus I cannot use temperature as a parameter. I know what the I know what the pressure is, I do not know what the temperature is, and I do not know what the volume is. So, how do we do that? We make use of the fact that if it is a vapor, then the quality has to be 1. Okay. Let us first find out the saturation temperature. So, I want to know the temperature of steam corresponding to P equal to pressure 1, which is the value we just found, and X equal to 1. All right. Let us see, let us run this. So, temperature corresponding to this saturation is 154 degree Celsius. So, this particular point is at 154 degrees Celsius. Okay. Now, in order to plot this point, I also need to plot the volume. Fine, let us find the volume. So, we need to find the volume of steam. So, volume here refers to the specific volume. See, in thermodynamics we do not do absolute volume calculations, we do specific volume calculation. So, it is understood that the function that we have called here corresponds to specific volume and not total volume. So, this is specific volume. Volume of steam corresponding to P equal to pressure 1 and x equal to 1. So, naturally we expect that volume to be less than 0.4 because this volume was 0.4, and from the plot we see that this particular volume has to be less than 0.4. Let us see. It is less than 0.4, in fact it is 0.3546. And obviously press 2 is naturally equal to press 1. This is what we have prescribed. We want to know the conditions at the same pressure, but at saturation. Okay. So, this is what we will write. So, these are the points. Let us try to plot point 2. So, we go to plot, overlay plot. Now, we select on the x axis we have volume, on the y axis we have temperature. So, it will plot all the points that it sees over here. It has joined it by a red line, but I mean it does not matter. Actually, it is not a process. When you join 2 points, usually corresponds to a process. So, thus this point is on the isobar. Say actually we did not plot the exact isobar, we plotted the 540 kilopascal isobar, but the reality, in reality the pressure is 530.4, my bad. So, it is 530.4 anyway. So, it is slightly below this. Obviously, if at a lower pressure it will correspond to a slightly lower point, no problem. So, this is how we have found this point. Now, suppose someone tells you, okay, very good, but I want to now find out what is the specific volume of liquid at this point. For this, fine, we say vol 3 is equal to volume steam P equal to press 1 and x equal to 0. X equal to 0 corresponds to pure liquid. Press 3 is equal to press 1, because we are specifying that the volume has to be, that the pressure has to be constant. Temperature obviously will be equal, but just for the completeness, temp 3 equal to temperature steam P equal to press 1, x equal to 0. So, when we solve this, it now yields a much smaller specific volume, because we know that water, when it is in liquid, the density is 10⁻³ approximately, okay, depending on the temperature and all this thing. So, the specific volume will be 1 by density. So, it is order of magnitude 10⁻⁻³. So, this is 10⁻⁻³. All these regions are in 10⁻⁻³. Okay. So, logically it is okay, everything is fine, and once again we can plot this on the plot. Now, if I attempt to find out the volume of at saturation using the pressure and temperature, it will throw me an error. Okay. Suppose I want to find out what the volume of this point is. I cannot, because at this particular point, on all these points, the temperature and pressure are constant, because all these points correspond to a zone in which there is latent heat of absorption. So, any increase in temperature will not occur in this zone. At a fixed pressure, the temperature will also be fixed during the change of phase. So, I cannot simply obtain a volume. So, let us say vol 4 equal to volume of steam corresponding to P equal to press 1 and T equal to temp 3. See, obviously pressure 1, which is this isobar, and temp 3, which is corresponding to this particular temperature of the line, because temp 3 was the temperature of steam at x equal to 0. This obviously means that temp 3 is the saturation temperature. Obviously, both the quantities that I am supplying to this function are the saturation quantities, and this will throw me an error. Okay. It says P is the saturation pressure corresponding to the given temperature, properties cannot be determined from this information. So, it throws an error which says that inside this saturation point, you cannot give me pressure and temperature as two independent quantities to find out the property. Obviously, I can then have some other quantity. I can choose either temperature and pressure and then the quality. Let us write x equal to 0.5. So, it is half liquid and half vapor. Half of the mass is liquid, half of the mass is vapor. Let us see what the specific volume is. There you go, it is 0.1778. So, it is somewhere over here. Okay, this point corresponds to 50% mass of liquid converted to 50% mass of vapor. So, inside the dome, what we have seen theoretically that you have to give two independent properties, one of which can be temperature or pressure, the other has to be quality. This is how we do the calculations. Alternately, we can also find out the quality. Okay. Let us say x, so qual 5 is equal to quality steam P equal to press 1 and let us say V equal to. So, now obviously I have to give the function some specific volume which lies between these two bounds. Let us say it is 10⁻². We clearly see that 10⁻² specific volume is inside the dome corresponding to this. So, let us write V equal to 0.01. So, it will give us some quality which is between 0 and 1 and it is obviously less than 0.5 because we have seen 0.5 lies somewhere over here. So, the quality at 5 is 0.02519. Thus, even with the help of volume, we were able to find out the quality. So, volume is also the property, the specific volume is also the property which we can use inside the superheated dome, inside the saturated dome. Outside the saturated dome, you can use temperature and pressure, no problem. You can use temperature, pressure, volume, any of this. Outside the saturated dome, there is no use of quality because quality does not exist, everything is a vapor. So, obviously, if you try to call quality for a point which is outside, it will give you some kind of indication that whatever you have just input, let us say pressure equal to pressure 1 and T equal to temp 1, because we can this press 1 and temp 1 corresponds to this particular quantity which is outside the saturated dome, it is in a superheated region and hence I can give P and T separately. Let us see what it gives. It gives us qual 6 equal to 100. So, 100 indicates to the user that whatever you have just given does not lie between 0 and 1, it is superheated. 100 does not mean the quality is 100, it is just a number which the software has encoded to indicate to you it is an absurd quantity which is more than 1 and hence you have to interpret that as superheated. Similarly, if you give something in the subcooled region, so we have given this as the condition P equal to press 1 which is this pressure and specific volume is 10⁻³ somewhere over here. Okay. So, let us see what the quality we obtain. It is -100 indicating to the user that whatever point you have just given me is in the subcooled liquid, it is not in the saturated dome. So, this is how you have to make use of the software. Ideally, you would look up the tables in the olden days, or if you go even further you would look in the Moliere charts. In the Moliere charts you have all this information, but now you can look up all these properties and do some simple calculations by means of a computer. In this case we are using the software EES. There are other softwares which make use of other thermodynamic tables, no problem. All these databases have been made by very renowned very renowned organizations like ASHRAE, NASA and all these things, and it was meant to be used with a computer for very fast calculations, for very accurate calculations. Usually these hand calculations may not be so accurate. So, anyway, we will throughout this course we will make use of this kind of computer aided means to solve various kinds of problems. So, I suggest you download a demo version of this, and like I have shown, try to do simple calculations, try to compare the calculations against that of a book, find out the volumes and all, and hopefully you will appreciate how simple life becomes. But one should not forget that whatever we are doing is motivated by our own understanding of thermodynamics. It is not that the computer is doing something for us. We are telling the computer that, okay, give me this value, give me that value. The computer is merely a slave for us. It is just a tool which we are using. With this note, I will see you next time. Thanks.